You have almost certainly heard that we've explored 5% of the ocean. That number is a lie. Not because it's too big, because it hides 3 different truths inside one sentence. There is a map of the entire seafloor hanging in classrooms right now, every ridge and trench in place, and almost none of it has ever been seen. Humans have laid eyes on a piece of the deep ocean smaller than a small U.S. state. 70 years of diving. And that's the total. So which is it? Mostly mapped or almost entirely unseen? And one word decides everything. You've seen the number. It's on posters and museum walls, in textbooks, in the first 10 seconds of 1,000 videos just like this one. We have explored 5% of the ocean, 95% unknown. Sometimes it's 95, sometimes 80. Sometimes it climbs all the way to, we know more about space. It always sounds precise. It always sounds like someone somewhere stood at the edge of the water with a clipboard and measured exactly how much of the sea we've figured out. Nobody did. That's the first crack in the whole thing. And once you see it, you can't stop seeing it. Try to trace that 5% back to its source. Follow it upstream from the video to the article the video copied to the article that one copied, and you don't arrive at a study. You arrive at a fog. The number gets repeated because it's already being repeated. It has the shape of a fact without the spine of one. No date, no method, no name attached. It's the kind of statistic that survives precisely because it's vague enough that nobody can prove it wrong. And nobody can prove it right either. So before we argue about whether it's 5% or 50, we have to ask a smaller, sharper question. The one the number is quietly avoiding. What does explored actually mean? Because here's the trap. Explored isn't one thing. It's at least 4 things wearing the same coat. And each of the 4 gives you a completely different answer. Picture 4 bars on a screen. Same width, wildly different heights. Label the first one mapped. Not, have we been there? Just, do we have a chart of the shape of the bottom? Do we know where the mountains are? Where the trenches drop? Where the plains stretch flat for 1,000 kilometers? That's a real question with a real answer. And we'll get to how strange that answer is in a moment. Label the second bar seen. Completely different. Has a camera or a human eye ever actually looked at that patch of seafloor? Not sensed it from a distance, looked at it, watched what was sitting there in the dark. Label the third bar sampled. Different again? Have we physically touched it, pulled up a rock, trapped an animal, drawn a jar of water from that exact spot, and carried it to the surface to study? And the fourth bar, understood. The tallest ambition and the shortest bar. Do we actually know what lives there? How it feeds? How it connects to everything else? What it does to the planet you're standing on right now? 4 bars. 4 meanings. And the 5% number takes those 4 wildly different heights, crushes them together, and hands you one flat line as if the distinction never mattered. That's the mechanism of the lie. Not a false number. A blurred question. Now watch what happens when you refuse the blur and take the meanings one at a time. This is where it gets uncomfortable, because the answers don't just differ. They contradict each other. Start with mapped. If you mean, is there a map of the entire ocean floor? Every basin, every ridge? The honest answer is yes, all of it. There is a map of the complete seafloor, and you have almost certainly seen it. The deep blue relief image, the wrinkled skin of the planet under the water, mountain chains longer than any on land snaking across every ocean. That map is not a guess about part of the floor. It covers 100% of it. So in that sense, the ocean isn't 5% explored. It's fully charted. The 5% number isn't just imprecise there. It's the opposite of the truth. Hold that thought because it's about to collide with the next one. Take the second meaning, seen. Has a human being or a machine carrying a camera actually laid eyes on the deep sea floor, not the map, the real ground, the real dark, the thing itself. And here the number doesn't shrink to 5%, it collapses. It falls through 5%, through 1%, through a tenth of a percent, and keeps going. The best estimate we have for how much of the deep sea floor has ever been visually observed is less than 1,000th of 1%. We'll sit with that figure properly later because it deserves its own reckoning. For now, just feel the whiplash. By one honest definition, we've covered the entire ocean. By another honest definition, we've seen almost none of it. Same ocean, same week, both true. So the popular number isn't wrong in the ordinary way, where you nudge it up or down to fix it. It's wrong in both directions at once. It is far too small, if you mean the map. And it is enormously, absurdly too large, if you mean what we've actually looked at. 5% sits in the middle like a compromise nobody negotiated. Too generous for one truth, too stingy for the other, accurate for neither. That's the part that should unsettle you. Not that we know less than we thought. That the single number everyone repeats is built to stop you from asking the only question that would reveal how strange the real situation is. And the strangeness runs deeper than seen. Push into the third meaning, sampled, and the ground gets thinner still. Having a photograph of a patch of seafloor doesn't mean anyone touched it. To sample the deep, you have to physically reach down through kilometers of black, freezing, crushing water and bring something back. A scoop of sediment, a trapped animal, a core of rock. The fraction of the deep ocean we physically handled is a subset of the tiny fraction we've even seen. A sliver of a sliver. And the fourth meaning, understood, barely translates into a percentage at all. You can film a place and still have no idea how it works, what eats what, how it breathes, what it's doing to the carbon in the atmosphere above it. Understanding isn't a patch of ground you can shade in on a map. It's a different kind of question entirely, and by that measure, the honest figure isn't small. It's closer to a shrug. So the clean 5% statistic has quietly dissolved into 4 different numbers that don't agree, don't line up, and don't even measure the same kind of thing. One says 100. One says a fraction of a percent. 2 of them barely fit on the scale at all. Here's what you actually walk away with. You started with one confident, tidy fact. 5% explored. And it turns out that fact was hiding 4 separate mysteries in a trench coat, hoping you wouldn't check its pockets. Trade the lie for the honest version, and you don't get a smaller answer. You get 4 better questions. How much of the seafloor do we really have a map of? And what kind of map is it? How much have we actually seen with our own instruments? How much have we ever touched? And how much of any of it do we genuinely understand? Those 4 questions are the whole story from here. Every chapter is going to hunt down one of them and drag back the real number, the real reason, and the reason that number is so much stranger than the myth it replaces. We're going to start with the biggest one, the claim that sounds least believable and turns out to be true. Because before we confront how little of the deep we've ever seen, we have to deal with something that shouldn't be possible given everything I just told you. There is a complete map of the ocean floor, all of it, nothing left blank. It hangs on classroom walls and loads in a second on your phone. And it shows you the shape of ground that no ship has ever crossed and no eye has ever watched. A full map of a place we've barely visited. That map should not exist. And the way it was made is the first genuinely strange thing about this entire story. How do you draw a map of a mountain nobody has ever been to? Not estimated, not sketched from a passing guess, A real map, detailed enough to show a peak taller than anything in the Alps, sitting under 3 kilometers of black water in a stretch of ocean where, as far as we know, no ship has ever stopped, no camera has ever descended, and no human being has ever laid eyes on the thing at all. That map exists. It exists for that mountain and for every mountain like it, across every ocean on Earth. Pull up a seafloor map right now, and you can scroll across the entire planet's underwater terrain without hitting a single blank space. The mid-ocean ridges, 65,000 kilometers of them, the longest mountain chain on the planet, wound around the globe like a seam. The trenches plunging down at the edges of continents, the vast flat abyssal plains between them, the flattest surfaces that exist anywhere on Earth. It's all there. Shaded, colored, complete. Now hold that against what I told you a moment ago. Less than 1,000th% of the deep sea floor has ever been visually observed. Both of those things are true at the same time, and if you're paying attention, they should not fit together. A complete map of a place almost nobody has seen. That's not a contradiction you can wave away. That's a clue. Because the only way both statements can be true is if that map was made by a method that never required going there at all. And that's exactly what happened. Here's the assumption we have to break first, because almost everyone carries it without noticing. When you picture mapping the ocean floor, you probably imagine a ship or a submarine physically passing over the terrain, sending something down, waiting for it to come back, building up the picture line by line, the way you'd map a cave by walking through it. That does happen. We'll get to it, and it's slow and brutal and expensive. But that method has nowhere near enough reach to have drawn the complete map you've seen. Not even close. If the full seafloor map had to be built ship by ship, passing over every point, it would still be mostly empty. Most of it, the map was never made from below. It was made from above, from space, by a satellite that never touched the water and never once looked at the bottom. I know how that sounds. A satellite hundreds of kilometers up that somehow maps the shape of ground buried under kilometers of opaque ocean. Ocean that light can't punch through, that radar can't see into. You can't photograph the seafloor from orbit. The water blocks it completely. So how does a machine in space chart a mountain range it fundamentally cannot see? It doesn't map the seafloor. It maps the sea surface. And that turns out to be almost the same thing for a reason that's genuinely strange the first time you understand it. Think about what a mountain is. It's a colossal pile of rock, millions upon millions of tons of extra mass concentrated in one place. And mass has a gravitational pull. Every object with mass tugs on everything around it. And a mountain the size of a small country tugs hard. On land, you don't notice, because everything's tangled together. But put that mountain on the seafloor, with kilometers of water sitting on top of it, and something quietly remarkable happens to the water. The extra gravity of the underwater mountain pulls the surrounding water toward it. Ever so slightly, water flows in and piles up over the peak. The ocean surface, the actual top of the sea, kilometers above the mountain, rises into a low, wide bump directly over the mass below. Not a wave. Not something you'd ever see standing on a boat. A swell in the sea surface itself, sometimes just centimeters high, spread across kilometers, held permanently in place by the pull of the rock beneath it. The seafloor writes its own shape onto the surface of the ocean, in gravity, and a satellite can read it. Sit with how strange that is. There's a mountain no one has ever seen, in water no one has ever crossed. But that mountain is bending the entire ocean above it into a faint permanent hill, and a machine in orbit can measure the height of the sea precisely enough to catch it. A dip in the surface means a trench pulling down below. A bump means a seamount or a ridge pushing mass up. Trace all those bumps and dips across the whole planet, and you can work backward, from the shape of the surface to the shape of the bottom that's sculpting it. You never have to go down there. The gravity does the reporting for you. That is how the map on the classroom wall exists. That's how we have a chart of 100% of the seafloor while having seen almost none of it. Nearly all of that global map, the mountains, the ridges, the broad shape of every basin, was inferred from the surface of the sea by satellites reading gravity's signature in the water. The floor was never touched, it was deduced. So when someone tells you the ocean is unmapped, they're wrong, and now you know exactly why. We have a map of all of it. In that sense, the 5% number isn't just off. It's backwards, but, and this is where the intrigue should replace the relief, read that sentence again. The floor was deduced, not observed, deduced. And a deduction is only ever as sharp as the thing it's built from. That map wasn't made by looking. It was made by inference, by reading a shadow the seafloor casts upward into the water. And the moment you realize that, a new and much more uncomfortable question opens up underneath the first one. Because a shadow is not the thing. A shadow smears. It blurs the edges. It tells you something large is there without telling you what, exactly, or in what detail. If our complete map of the ocean floor was built from gravity bumps at the surface, then the real question isn't whether the map exists. It clearly does. The real question is, how good is it? How much detail can a method like that actually resolve? When you zoom in on that beautiful, complete planet-wide map, when you push past the broad shape of a mountain and ask to see the mountain itself, its slopes, its base, the ground around it, the things that might be living on it, what do you actually get? Do you get a photograph or do you get a rumor? Here's the part that quietly undoes the victory. That full map, the one that proves the ocean isn't unmapped. It's real, and it's an astonishing piece of science. And it's also a low-resolution guess, dressed up in confident color. It can show you that a mountain is there. It struggles to show you anything small. And small, at the scale of the ocean, includes almost everything that would actually matter if you were trying to understand the place, instead of just sketch its outline. So we've answered the first of our 4 questions, at least on the surface. Is there a map? Yes, all of it. But we've done the thing this whole story keeps doing. We've solved one mystery and torn open a worse one directly beneath it. The map exists. Now I have to show you what that map can't see. Because the gap between we have a map of everything and we can actually make out what's down there is enormous. And hiding inside that gap is the reason a satellite can chart a mountain and still miss a feature the size of a city sitting right beside it. To understand how blurry that map really is, and why the blur matters more than the map, we need to look closely at how the satellite reads that bump in the sea. And at the hard limit built into the method, the one no amount of cleverness has fully beaten yet. A bump in the ocean the width of a large city, and only a few centimeters tall. That's the signal. That's the entire thing a satellite is trying to catch when it maps the seafloor from space. Not a wave, not a swell you could ever see or feel. A permanent rise in the sea surface, so faint that if you were standing in a boat directly on top of it, floating over a mountain 3 kilometers below, you would notice absolutely nothing. The water would look flat. It would feel flat. And it would be lying to you by a few centimeters, and those few centimeters would be the only evidence from the surface that a mountain existed at all. The fact that we can measure that bump is one of the quietly absurd achievements of modern science. Think about what's stacked against it. A satellite, hundreds of kilometers overhead, moving at thousands of kilometers an hour, trying to measure the height of a churning ocean. An ocean with actual waves on it, Real waves, meters high, wind-driven chaos rolling across the whole surface, and inside all that noise, it has to pick out a stationary rise of a few centimeters spread across kilometers. It's like trying to measure the exact height of a single step on a staircase, while the whole staircase is being shaken from across a football field by reading the shadows. And yet it works. It works because that faint bump doesn't move. The waves come and go, but the gravity swell sits there permanently, anchored to the mass below. Measure the same patch of ocean again and again, thousands of times, and the random waves start to average out. The chaos cancels itself. What's left, slowly emerging from the noise, is the shape that never changes. The fingerprint of the sea floor pressed into the surface of the sea. For 30 years, that's how the global map was built. Older satellites measured sea surface height along single lines, straight tracks laid down beneath the satellite's path. And from those lines, scientists reconstructed the gravity field. And from the gravity field, the shape of the bottom. It gave us the map, you know. It gave us the entire planet's underwater terrain. And it did it at a resolution of roughly 12 to 16 kilometers. Stop on that number, because it's the whole point, and it's easy to let it slide past. 12 to 16 kilometers of resolution. That doesn't mean the map is accurate to within 12 kilometers. It means that anything on the seafloor smaller than about 12 to 16 kilometers across can effectively vanish. It's below the grain of the picture. Two features sitting closer together than that can smear into one. A structure narrower than that can dissolve into the background entirely. Let me make that visual, because a number like 16-kilometer resolution does nothing until you can see it. Picture a mountain on land. A real one, a serious peak. The kind that takes days to climb. Now imagine a map so coarse that the entire mountain occupies a single fuzzy dot, not the summit. The whole thing, the slopes, the valleys around it, the smaller peaks on its flanks, all of it compressed into one soft smudge with no internal detail. That's the older satellite map applied to the sea. It's not wrong. The mountain really is there, and the map really shows it. But it shows it the way you'd see a friend across a stadium in heavy fog. You can tell someone's standing there. You cannot see their face. You could walk right past a feature the size of a city, a canyon, a cluster of smaller seamounts, an entire underwater landscape. And the gravity map would show smooth, empty blue. So the complete map that felt like a triumph 2 minutes ago has a texture now. It's real, and it's blurred. And the blur is measured in kilometers, which means that we have mapped the entire ocean floor, and we have almost no idea what most of the ocean floor actually looks like up close, are, again, both true. The map gives you the outline of the planet's underwater skin. It does not give you the detail, and detail is where everything interesting lives, now. This is where it would be easy to end the chapter on a clean note. Old satellites, blurry map, moving on. But something changed recently. And it changed in a way that actually sharpens the mystery instead of solving it. A newer satellite came online at the end of 2022. Its job wasn't primarily to map the seafloor at all. It was built to study water on Earth, surface water, the height of the sea in far more detail than anything before it. But that same ability turned it into the best seafloor reading instrument ever flown. Instead of measuring sea surface height along single narrow lines, it measures it across wide swaths, in 2 dimensions at once, sweeping broad strips of ocean, with radar precise enough to catch height differences of centimeters. And when scientists took a single year of that data and processed it for gravity, the resolution of the seafloor map jumped from that old 12 to 16 kilometers down to around 8 kilometers. Roughly double the sharpness from 1 year of a better machine. And the moment they looked at the sharper picture, the seafloor did something that should make the back of your neck prickle. It filled up with mountains that weren't there before. Not new mountains, old mountains. Mountains that had been sitting on the seafloor the entire time that the blurrier map simply couldn't resolve. Too small to bend the surface enough for the old satellites to catch. Seamounts, underwater volcanoes, some of them a couple of kilometers tall. A couple of kilometers. That is not a pebble. On land, it would be a landmark you could see from another country, and we didn't know they were there because, at 16-kilometer resolution, they fell through the grain of the map and disappeared. The estimate before was something like 44,000 seamounts across all the world's oceans. The sharper view suggests the real number could be closer to 100,000. More than double. Tens of thousands of mountains, kilometers high, that existed on our complete map only as empty, smooth water, because the method that gives us the whole floor at once can only ever give it to us softened. And here's the twist that should stay with you. Making the map sharper didn't make the ocean feel more known. It made it feel less known. Every jump in resolution reveals more that the old resolution was hiding, which means the smoothness of the map was never emptiness. It was ignorance, painted to look like knowledge. The blue that looked calm and finished was full of things we simply couldn't see yet. Sharpen the lens, and they appear, thousands at a time, which forces the obvious and unnerving question. What appears at 4 kilometers? At 2? At the scale where things actually live? Because there's a floor to this, a hard limit built into the whole approach, and it matters. Gravity mapping. Reading the seafloor through the bump it makes at the surface will never show you the small stuff. It can find a mountain. It cannot find a boulder, a vent, a ledge, an animal, a wreck, a canyon a few hundred meters across. The physics won't allow it. A feature has to be big enough, massive enough, to leave a mark on the sea surface centimeters high and kilometers wide, or the satellite has no way to know it's there. So no matter how good the satellites get, this method has a permanent ceiling. It gives us the shape of the planet's underwater terrain in broad strokes and stops, by design, long before the detail that would let us say we'd actually seen anything. Which means the entire global map, the thing that proves the ocean isn't unmapped, tops out at a level of detail where a 2-kilometer mountain can hide. That's the best the "we've mapped it all" version of exploration can ever do from above. So if you want more than the outline, if you want the ground itself, in real detail, sharp enough to see a canyon, or a ridge, or the actual texture of the bottom, you cannot do it from space. You have to leave the satellite behind. You have to get in a ship, go out over the water, and drag the map up from below, one narrow strip at a time. That's the only method that gives you true resolution. And the moment you switch to that method, the number that was a proud, complete 100% collapses to something far smaller and far more honest. Because when we stop inferring the floor from orbit and start actually measuring it from the water, the amount of ocean we've really charted in sharp detail turns out to be barely a quarter. And even that took decades of the hardest, slowest mapping work on the planet. Everything I've shown you so far, the complete map, the mountains read from gravity, the whole planet's underwater terrain glowing on a screen, all of it came from above, from satellites that never touched the water. And it gave us the outline of the world's seafloor without a single ship needing to cross most of it. Now throw that method away, because if you want the real map, not the blurred gravity sketch, but the sharp one, the one that can actually show you a canyon wall or a ridge, or the shape of the ground the way you'd see a landscape on land, there's only one way to get it. You have to go out onto the water and measure the bottom directly. And the instant you do that, the number changes. It doesn't shrink a little, it falls off a cliff. Because measuring the seafloor from a ship is nothing like reading it from space. From space, you get the whole planet in broad strokes, all at once, for free, forever. From a ship, you get one strip, one narrow ribbon of bottom, directly beneath the hull, as the vessel moves across the surface at the speed of a bicycle. Here's how it actually works and why it's so punishing. A survey ship carries a sonar system mounted on its underside, a multi-beam echo sounder. It sends a fan of sound pulses down into the water, spreading out sideways beneath the ship like a wide blade. Those pulses travel down, hit the seafloor, and bounce back. The system times how long each one takes to return, and because sound moves through seawater at a known speed, timing becomes distance, and distance becomes depth. Do that across the whole fan, thousands of pings a second, and you build up a detailed strip of the bottom. Real depth, real shape, resolution measured in a few hundred meters or better. Sharp enough to see the terrain instead of just the gravity smudge of it. But look at the geometry of that, because the geometry is the whole tragedy. The sonar fan only covers a strip as wide as it can reach to either side of the ship. In deep water, that strip might be a handful of kilometers across, sometimes less. And to map the next strip, the ship has to physically drive over to the next strip and do it again. And the next. And the next. You are painting the floor of the ocean with a brush, the width of a road, one pass at a time. And the canvas is the size of every ocean on Earth combined, more than 70% of the surface of the planet, kilometers deep, most of it nowhere near anywhere anyone has any reason to sail. Now feel the scale of that problem. A single ship moving at survey speed, covering one strip at a time, trying to paint an area that covers most of the planet. It's the kind of task where you can work for years, sail tens of thousands of kilometers, and barely darken a fraction of the map. And that's exactly what's happened. There's a global effort underway right now to do precisely this, to assemble every scrap of high-resolution sonar data from research vessels, navies, survey companies, even fishing and cargo ships willing to run their sounders and donate the readings, and stitch it all into one true ship-measured map of the entire ocean floor. The goal is to finish the whole thing by 2030. A complete high-resolution chart of the planet's underwater surface, built the hard way, from below. When that effort started, back in 2017, they took stock of how much of the seafloor had already been mapped to modern standards. Sharp, reliable, ship-grade detail. The answer was about 6%. 6%, after all of human history. After every naval expedition, every research cruise, every survey voyage ever run, all the sonar ever dragged across the sea, 6% of the ocean floor had been properly measured. That's the honest starting line. Not the gravity outline, which covers everything. The real detailed map covered 6% of the bottom. And here's the thing that should recalibrate you. That number is the answer to a completely different question than the map from space answered. From orbit, how much have we mapped was 100% blurred. From a ship, how much have we mapped in real detail was 6%. Same ocean. Same word, mapped. Two answers that are almost 100 points apart. This is the 4 bars problem from the very beginning, showing up exactly where the blueprint said it would. The word does the lying. The method decides the truth. So where are we now? The effort has been running for years, pulling in data from more than 180 organizations, adding millions of square kilometers a year, and it's worked. The number has climbed hard. By the most recent reckoning, as of mid-2025, the share of the seafloor mapped to modern standards has risen from that starting 6% to about 27%. 27%. Call it a quarter of the ocean floor, charted in real detail, for the first time in the history of the species. That's genuine, and it's fast, and it represents a staggering amount of work. Ships crisscrossing the planet, in-transit vessels running their sounders on long ocean crossings, an entire global patchwork being assembled one strip at a time. Now hold that 27% up against the 5% myth we started with, and watch how badly the myth misleads you in both directions at once. If you meant the gravity map, 5% was absurdly too low. The real figure is everything. If you mean the detailed, ship-measured map, 5% is too low again, but only barely. The real figure is around 27. The myth undershoots the outline by 95 points and undershoots the real map by 20 odd. It is wrong high, it is wrong low, and it is never once right. There is no definition of mapped that makes 5% the correct answer. None. But, and here's where the real weight of this chapter lands, don't let that 27% feel comfortable. Because look at what it took to get there, and look at what's left. Roughly 3/4 of the ocean floor still has no sharp map. 3/4. After the biggest coordinated mapping push in human history running for years, with global participation, most of the bottom of the planet remains uncharted in real detail. Still just the gravity smudge. Still just the outline read from a bump in the sea. And the reason it's so slow isn't incompetence or neglect. It's that geometry problem, unforgiving as ever. One ship, one strip, a bicycle's pace, across an area the size of most of the world. The vessels are extraordinary. The sonar is extraordinary. The physics of covering that much ground, that narrowly, is simply brutal. You cannot rush the size of the ocean. There's a quiet twist buried in how they're even managing to move the number at all. A lot of that new coverage doesn't come from dedicated survey missions steaming out to blank spots on purpose. It comes from ships that were going somewhere anyway. Research vessels on their way to other jobs, crossing open ocean, running their sounders during the transit, and donating whatever strip happened to be under them. The map is being filled in partly by accident, by the incidental tracks of ships passing over unmapped water on their way to do something else. Which tells you something bleak about the parts no ship ever crosses on the way to anywhere. Those blanks don't get filled by accident, and there are a lot of them. So we've got our second real answer now, and it's sharper and stranger than the myth. How much of the ocean have we mapped? It depends entirely on what you'll accept as a map. The whole thing if you'll take a blurred gravity outline, about 1/4 if you demand real detail. Nowhere close to the whole either way you cut it, and the myth's 5% is simply wrong on every reading. But notice what we still haven't touched. We've been talking about maps this entire time. Gravity maps, sonar maps, resolution, coverage, percentages of the bottom charted. And a map, even a perfect one, even a sharp 27% of it, is not the same as having been there. A sonar ping tells you the shape of the ground. It does not tell you what's sitting on it. It doesn't show you color, or movement, or the animal crossing that ridge, or whether anything is alive down there at all. A map is the shape of a place, with everything that makes it a place stripped out, which means that even the 1/4 we've mapped in beautiful detail is, in the way that matters most, still unseen. We have the shape of it. We've never looked at it. And the gap between mapping the seafloor and actually laying eyes on it is about to make everything up to now look like the easy part. Here's a sentence that shouldn't be able to follow the last chapter, and does. We have a sharp, detailed sonar map of about 1/4 of the ocean floor. And almost none of that 1/4 has ever been seen. Read it twice, because your brain will try to smooth it over. Mapped, but not seen. Those feel like they should be the same thing. You mapped it. Surely that means you were there. You looked. You know what it looks like. That's the assumption, and it's wrong. And the gap between those two words is the single biggest thing the 5% myth hides from you. A sonar map is not a look at the seafloor. It's the shape of the seafloor with everything else deleted. Remember how the map gets made. Sound goes down, bounces off the bottom, comes back, and the timing gives you depth. That's all it gives you, depth. The height of the ground, point by point, until you've built a relief model of the terrain. It's genuinely detailed. It can show you a ridge, a canyon, the slope of an underwater mountain, but it is blind in every way that isn't shape. It has no color, no light, no life. A sonar ping crossing a patch of seafloor can't tell you whether that patch is bare rock or carpeted in creatures, whether it's dead mud or a thriving colony, whether something just moved across it or nothing has moved there in 1,000 years. It registers the same either way. The ground is the ground. Whatever's living on it is invisible to sound. So picture what mapped but not seen actually means down there. There is a ridge on the seafloor, real, charted, sitting in the detailed quarter of the map, its shape known to within a few hundred meters. Scientists can call up its exact contours on a screen, and no human eye and no camera has ever once looked at it. Nobody knows its color. Nobody knows what's growing on it, hunting on it, drifting past it. We know the shape of a place we have never seen. We've built a precise map of a landscape nobody has ever laid eyes on. That's not a small technicality, that's most of the mapped seafloor. The shape is known. The place is a stranger. Which forces the real question, the one this whole video has been circling. Forget maps for a second. Maps are the shape, not the thing. How much of the deep ocean have we actually looked at? Put a camera on it, or a human eye behind a window and genuinely observed it, not sensed from a distance. Seen, and this is where the number stops being merciful. In 2025, a study set out to answer exactly this. Not how much have we mapped? How much have we visually observed? The researchers went after every deep-sea dive record they could gather, reaching all the way back to 1958, the earliest days of deep submergence, human-crewed submersibles, remotely operated vehicles, the ROVs with cameras and lights that crawl the bottom, towed camera systems. Every record where something with an eye or a lens actually went down into the deep sea and looked. They pulled together tens of thousands of dives, around 43,000 of them, spanning nearly 70 years, across the waters of well over 100 countries. Then they estimated how much total seafloor all of those dives, added together, across all that time had actually seen. The deep sea here means everything below 200 meters, the depth where sunlight gives out and the real dark begins. That zone covers about 2/3 of the entire surface of the planet. It is, by a wide margin, the largest living space on Earth. That's the denominator. That's what we're measuring against. And the answer? 70 years, 43,000 dives, the combined effort of every deep diving nation in history? The answer is less than 1,000th of 1%. Let that number sit, because it's so small it barely registers as real. Not 1%, not 0.1%. Less than 1/1000th of 1% of the deep seafloor has ever been visually observed. Write it as a decimal, and you're counting zeros after the point before you get to a digit that isn't zero. That is the honest answer to how much of the deep have we actually seen. Essentially, none of it. Now make it a picture, because a number that small slides off the mind. The study reached for a comparison, and it's a good one. Take all the deep seafloor humans have ever laid eyes on, every dive, every ROV crawl, every submersible window, 70 years of it, summed into one total, and it comes out to roughly the area of the U.S. state of Rhode Island. One small state, That's the entire visual record of the deep ocean. A patch about that size. Seen. And spread around it, in every direction, the largest habitat on the planet, 2/3 of the surface of the Earth, never observed at all. Feel the whiplash against where we were 3 chapters ago. We started with a complete map of the whole sea floor, and it felt like we'd basically conquered the place. Now we're standing on the real question: what have we seen? And the answer is a patch the size of Rhode Island against an area the size of 2/3 of the planet. That is the true distance between mapped and seen. That is the gap the myth was built to hide. And here's why this reframes everything. The 5% number, whatever else is wrong with it, is enormous compared to the truth. 5% of the deep ocean seen would be a staggering achievement, thousands of times more than we've actually managed. The real figure isn't 5%, it's less than 1,000th of 1%. The popular lie isn't just imprecise here. It overstates what we've seen by a factor of thousands. When people repeat, "we've explored 5%, they're being wildly generous. The honest version is far darker. We've explored, in the sense of actually looking, almost nothing. Now, you should be skeptical of a number that dramatic, and the researchers were too. So they built in a cushion. They pointed out that even if their estimate were off by a full order of magnitude, 10 times too low, meaning they'd somehow missed 90% of all the observing humanity has ever done, even then, the total seen would still come in under 1/100th of 1%. The conclusion doesn't move. You can be generous. You can assume huge amounts of unrecorded diving. You can stack the deck in favor of "we've seen a lot," and the answer is still a rounding error away from zero. The figure isn't a fluke of bad bookkeeping. It's robust. The deep ocean is, by the measure that matters most, unobserved. And this reframes the mapped quarter too. That beautiful 27% from the last chapter. The sharp sonar map, the real achievement, sits almost entirely inside the unseen. We have the shape of a quarter of the seafloor, and we've looked at essentially none of it. The map is a promise we haven't kept. It says here is the terrain, and we have never gone to find out what the terrain holds. So the picture has inverted completely from where we began. We have a full outline of the planet's floor, read from space. We have a detailed map of a quarter of it, dragged up by ships. And we have actually seen a piece the size of one small state, mapped everything, charted a quarter, observed almost nothing. 3 numbers, 3 definitions, and the myth got all 3 wrong. But a figure this extreme, less than 1,000th of a percent after 70 years, demands its own explanation, because your instinct is probably rebelling right now. 70 years, 43,000 dives, submarines, robots, decades of ocean science, whole institutions built around going down there. How on earth does all of that add up to a patch the size of Rhode Island? Where did all those dives go? How can that much effort leave that little scene? The answer is hiding in the shape of a single dive, in how pitifully little ground one trip to the bottom actually covers. And once you see the geometry of it, the tiny number stops being shocking and starts being inevitable. 43,000 dives, nearly 70 years. Every deep diving nation on Earth. And the total comes out to a patch the size of one small state. Your instinct says those numbers don't fit. That much effort should add up to more. So let's follow the effort down and find out where it all went. Because the answer isn't that people didn't try. It's that a single dive into the deep sees almost nothing. And once you understand why, the tiny total stops being a shock and becomes the only possible outcome. Go down with one of them, an ROV, a remotely operated vehicle, the workhorse of deep exploration. It's tethered to a ship far above by a cable kilometers long, and it carries lights and cameras down into water that has never known light. Getting it to the bottom is not quick. In deep water, the descent alone can eat hours. The vehicle sinking slowly through the black, the ship holding position at the surface, the cable paying out, and nothing to see the entire way down but marine snow drifting up through the lights. Hours just to arrive. And every one of those hours is expensive, crude, and finite. Then it reaches the bottom, and here's the part that matters. Its lights only reach so far. In the clearest deep water, a camera can see a cordon of illuminated ground. A small circle, maybe a lane carved out of the dark. Beyond that lit patch, nothing. The vehicle moves forward slowly, deliberately, and it sees the ground the way you'd see a forest floor by crawling through it at night with a flashlight. A ribbon of illuminated bottom passing beneath you, everything outside the beam, unseen. And it moves at a crawl. You cannot race an ROV across the seafloor. You'd blur the cameras, miss everything, and risk the vehicle. So it inches, a slow-moving light dragging a narrow-lit ribbon across the floor for a few hours of bottom time before it has to come back up. Now add those ribbons together. That's what the study did. Take every dive, all 43,000, each one seeing its own thin-lit strip of ground, and lay all those strips side by side. Sum the entire visual footprint of human deep-sea exploration since 1958. All of it. Every flashlight beam that has ever crawled the deep combined. And you get the patch the size of Rhode Island. That's the geometry. That's the whole answer. It's not that people didn't dive. It's that each dive sees a strip about as wide as a road and about as long as a slow afternoon allows, and even 43,000 of those strips, stacked across 70 years, cover a piece of the 2/3 of the planet deep sea. So small, it barely marks the map. The effort was real. The effort was enormous. The ocean is just so much larger than the reach of a single light that the effort disappears into it. The researchers actually ran the estimate 2 different ways, and this is worth understanding because it's where the number gets its spine. One approach worked from the dives themselves. How much area does each type of vehicle cover per dive, multiplied across all the dives? That gave one figure. The other approach worked from time, total hours spent at the bottom, multiplied by how fast the vehicles move and how wide their field of view is. A completely different route to the same question, and the two methods didn't wildly disagree and force a guess. They converged. Both landed in the same tiny territory under that 0.001% ceiling. When two independent methods walk in from different directions and meet at the same impossibly small number, that number stops being a guess. It becomes hard to escape. And they went further because they knew how unbelievable it sounds. What if the records are incomplete? Not every dive in history is neatly logged in a public database. Some are private, some are old, some belong to militaries or companies that never shared them. Fair. So they asked, what if we've undercounted massively? What if the true amount of observing is 10 times what we can document? And even then, even multiplying the seen area by 10, the total still comes in under 1/100th of 1%. You can hand the deep ocean a 10-fold benefit of the doubt, and it barely moves off zero. That's how much room there is between what we've seen and the size of the place. 10 times almost nothing is still almost nothing. There's another detail in those records that quietly makes it worse, and it's about the quality of the seeing, not just the quantity. A large share of the deep-sea observations on the books, close to 1/3 of them, happened before 1980. And in that era, seeing the deep often meant something far cruder than what you're picturing. Grainy footage, black and white stills, low-resolution images from equipment that would look primitive today, capturing a murky frame of bottom and little else. So even inside that tiny Rhode Island-sized patch of observed seafloor, a big fraction was observed badly, glimpsed in poor light, in low resolution, in monochrome, decades ago. If you tighten the definition of seen to mean seen well, in color, in detail, the patch would shrink again. The already microscopic number has soft, blurry edges, and some of what counts inside it barely counts at all. So sit with what this means, because it's the emotional core of the whole story. We didn't fail to explore the deep sea through laziness or lack of trying. 43,000 times, people sent something down into the crushing dark to look. And the sum of all that looking is a patch you could drive across in an afternoon, against a wilderness the size of 2/3 of the planet. The smallness isn't a scandal of effort. It's a fact about scale. The deep ocean is so vast and the reach of any single descent so short that even 70 years of the hardest exploration humans know how to do vanishes into it like a coin dropped into a canyon. And here's the reversal that makes the number even more useful than it first appears. When something is this small, adding more of the same barely changes it. Run 1,000 more dives next year, a huge, record-breaking year of deep exploration, and you'd nudge the total by an amount too small to see on the chart. The problem doesn't yield to more of the same effort, because the same effort is precisely what produced almost nothing. That's not despair. It's the reason people are now trying to change the method entirely instead of just diving more, which is a thread we'll pull much later. But it starts here, in the geometry of a single crawling light. Now, so far I've been talking about all of this as if the tiny patch we've seen is at least spread evenly, as if that Rhode Island-sized sample is scattered fairly across the world's deep sea, a little here, a little there, a representative smear. If that were true, it would almost be reassuring. A tiny sample, but an honest one, giving us a fair if thin picture of the whole. It's not spread evenly, not remotely. And this is the part that should genuinely unsettle you, because it's not just that we've seen so little. It's where that little was seen. Because the flashlight beams didn't wander the globe at random. They clustered. They went back again and again to the same handful of places, in the waters of the same few wealthy nations, while entire ocean basins, vast stretches of the deep, thousands of kilometers across Hawaii, have essentially never been looked at all. So the honest picture isn't just, we've seen a tiny fraction. It's worse. We've seen a tiny fraction, and that fraction is a distorted, lopsided sample, crowded into a few countries' backyards, which means almost everything we think we know about the deep ocean, its life, its patterns, its rules, is built on a sliver that isn't even representative of the whole. And that changes how much we can trust the picture we've got. So far, the story has been about how little of the deep we've seen. Now it gets worse in a way you might not expect, because it's not just how little, it's where. And once you see where the looking happened, you have to question everything the looking supposedly taught us. Go back to that patch the size of Rhode Island. The entire visual record of the deep sea. Your mind probably pictures it scattered fairly across the world's oceans. A dive here, a dive there, sprinkled evenly enough that at least the sample is honest. A tiny window, but a clean one, giving us a fair, thin slice of the whole deep. That picture is wrong. The dives didn't spread out. They clustered, hard, in a way that quietly poisons a lot of what we assume we know. When the researchers looked at where all those deep-sea observations actually happened, the geography was lopsided to a degree that's hard to defend. Around 2/3 of all the visual records, 65%, came from the waters of just 3 countries: the United States, Japan, and New Zealand, most within a couple hundred nautical miles of those coastlines. Pull the lens back further, and it gets starker. just 5 nations, those 3 plus France and Germany, account for something like 97% of all the deep-sea dives ever made. 97%. Nearly the entire visual history of the largest habitat on Earth was recorded by a handful of wealthy countries, mostly looking close to their own shores, or the places their science programs happen to reach. Picture it on a globe, a world map of the deep sea, and you switch on a light for every place we've ever observed. A cluster flares around the United States, another around Japan, another around New Zealand, a few scattered points elsewhere, some European effort, some expeditions reaching further out. And then everything else stays dark. Enormous stretches of the Pacific, the Indian Ocean, the South Atlantic, the deep waters of the Southern Hemisphere, the basins far from any wealthy nation's coast, dark. Not dimly lit, dark. Whole regions of the deep larger than continents where the visual record rounds to nothing. Now put the two facts together, because this is where it turns from a curiosity into a real problem. We've seen less than 0.001% of the deep sea floor, and that sliver we have seen is crammed into the backyards of a few rich countries. So the sample isn't just microscopic, it's biased. It's a tiny window, and the window is pointed at a handful of the same neighborhoods, over and over. Here's why that should bother you more than the raw smallness did. A tiny random sample is still, in a limited way, honest. If you truly sprinkled 43,000 dives evenly across the world's deep sea, you'd have a thin picture, but a fair one, each region represented in rough proportion. You could cautiously generalize. But a tiny sample that's crushed into a few specific places isn't a fair, thin picture of the whole. It's a detailed picture of a few backyards, and a near total blank everywhere else. And we've been quietly treating that biased sliver as if it speaks for the entire deep ocean. Think about what that does to everything we believe about the deep. When a textbook tells you what life is like on the abyssal plains, or how deep sea communities are structured, or what's normal at 4,000 meters, where did that knowledge come from? Disproportionately. From the waters near the United States, Japan, New Zealand. Those are the places we've actually watched. So our sense of what the deep ocean is like is really a sense of what those particular regions are like, generalized outward across a planet's worth of water we've barely glanced at. We've been describing the whole deep sea from a few well-lit corners of it, and calling the description complete. And the deep sea is not uniform. That's the trap. If the bottom of the ocean were the same everywhere, same life, same conditions, same everything, edge to edge, then a biased sample wouldn't matter much. Look at one patch, you've effectively looked at all of them. But the deep isn't like that. It varies enormously from place to place. Different depths, different temperatures, different chemistry, different food falling from above, different geology beneath. A deep basin near New Zealand can be a fundamentally different world from an unvisited basin in the South Atlantic or the far Pacific. The animals differ. The communities differ. The rules can differ. So generalizing from the visited places to the unvisited ones isn't just thin. It may be actively wrong. We could be building our entire mental model of the deep on regions that turn out to be unusual, and mistaking them for the norm. The researchers put the scale of this bias into a comparison that lands hard. Imagine trying to understand all of life on land. Every forest, desert, grassland, jungle, tundra, every ecosystem on every continent, by studying an area roughly the size of a single city. And not a city you chose at random either. One particular city that happened to be convenient. Then imagine taking whatever you found in that one city and declaring it representative of all terrestrial life everywhere, forever. You'd never accept that. You'd know instantly that a single city can't tell you about rainforests and deserts and mountaintops, and yet that's the structure of what we've done with the deep ocean. A tiny, convenient, unrepresentative sample asked to speak for 2/3 of the surface of the planet. There's a reason the sample came out this way, and it isn't villainy, it's cost. This is the same wall we keep hitting from a different side. Deep sea exploration is staggeringly expensive. It takes specialized ships, specialized vehicles, cable systems kilometers long, trained crews, fuel, time. The kind of resources only a few wealthy nations and institutions have ever been able to sustain. So the countries that could afford to look, looked. And they looked reasonably close to home, or in the places their programs were set up to reach. Nobody sat down and decided to ignore the South Atlantic. It's just that going there costs a fortune, and the money and the machines lived elsewhere. The bias in the map is really a map of who could afford to go, which means the blank regions aren't blank because they're empty or boring. They're blank because nobody with the equipment had a reason or the budget to point it there. The darkness on that globe isn't the shape of what's unimportant. It's the shape of what's expensive to reach. And those are very different things, except that we've been treating them as the same, letting unvisited quietly stand in for nothing to see, when the truth is we simply haven't looked. So stack up what we've actually established now. We have a complete map of the seafloor, blurred, red from gravity. We have a sharp map of about 1/4 of it, dragged up by ships. We've visually seen less than 1,000th% of the deep, and that 1,000th% is lopsided, crowded into a few rich nations' waters, leaving basins the size of continents effectively unobserved. Every layer we peel back, the honest picture gets stranger and thinner than the myth promised. But under all of this sits a question I keep gesturing at and haven't answered. Why is it this hard? Not the geometry of a single dive. I mean the deeper reason. Why does looking at the deep ocean cost a fortune? Why can only a handful of countries do it at all? Why, in an age when we can land machines on other worlds and map the whole seafloor from orbit, is actually going down there and looking still so brutally difficult that 70 years of trying leaves us with a patch the size of one small state? The answer isn't money, not really. Money is just the symptom. The real answer is physics. There is a wall around the deep ocean, built out of pressure and cold and absolute darkness. And it is one of the most hostile barriers anywhere on or off this planet. That wall is why the map is so blurred, why the scene fraction is so small, why the sample is so biased, why all of it. And it's time to go down to it. Every problem so far, the blurred map, the sliver we've seen, the lopsided sample, has a single thing underneath it. Not money. Money is just what the real barrier costs. The real barrier is physical, and it's one of the most hostile walls anywhere on Earth. To understand why we've seen so little, you have to feel what it actually takes to go down and look. So let's descend, and let the reasons stack up on the way down, the way the pressure does. Start at the surface in daylight, in water that behaves the way your instincts expect. Now sink. The first thing you lose is the light, and you lose it fast. Water doesn't let sunlight through the way air does. It absorbs it, swallows it, color by color. Within a couple 100 meters, effectively all of the sunlight is gone. Not dim, gone. You cross into permanent darkness, and it never lifts again, no matter how much deeper you go. Everything below that, 2/3 of the surface of the planet, the entire deep sea, sits in blackness that has never seen a sunrise. That's the first reason looking is hard. There's nothing to see by. You have to bring your own light into a place that has never had any, and light only reaches as far as your lamps can throw it, which we already know is barely a lane of illuminated ground, keeps sinking. The next thing that changes is the one that does the real killing, and it's invisible: pressure. Every 10 meters you descend, the weight of the water above you adds roughly one more atmosphere of pressure, one more entire sky's worth of crushing force, stacked on top of the last. At the surface, you live under one atmosphere and never notice it. Go down 100 meters, you're under 11. A kilometer down, around 100. And the deep sea goes far, far deeper than that. At the bottom of the deepest trenches, the pressure climbs past 1,000 atmospheres, 1,000 skies, pressing in from every direction at once. Make that physical, because 1,000 atmospheres is just words until you picture what it does. That's a force great enough to crush a steel container like a can underfoot. It's why a submersible built to reach the deep isn't shaped like a submarine from a film. It's a thick sphere, because a sphere is the only shape that spreads that inward crush evenly enough to survive it. The window has to be a cone of material thicker than your arm, wider on the outside than the inside, so the pressure jams it into place instead of blowing it in. Every seal, every joint, every wire passing through the hull is a potential failure point where 1,000 atmospheres is waiting patiently to find the weakness. There is no forgiveness down there. A flaw that would leak a drop at the surface becomes a jet that can cut at depth. The deep doesn't attack you. It just presses everywhere, constantly, and waits for anything you built to give. And it's cold. Below the sunlit surface, the warmth goes with the light, and most of the deep sea sits just a few degrees above freezing, held there permanently. Cold that drains heat and battery power, cold that stiffens materials, cold that every machine and every crewed vehicle has to fight the entire time it's down. Darkness, then crushing pressure, then cold. And all three at once, all the time, with no relief and no exceptions. Now you can see why only a few nations have ever done this. It's not that the rest didn't care. It's that beating this wall requires machines built to survive conditions that exist almost nowhere else. Vehicles engineered to hold back 1,000 skies, carry their own light into permanent night, function in near-freezing dark, tethered to ships by cables kilometers long, all without a single fatal flaw. That is monstrously expensive and monstrously hard. And it's the real reason the scene fraction is a sliver and the sample is lopsided. The bias in the map is the shape of who could afford to fight this wall. The wall came first. Here's the reframe that changes how the whole thing feels. We've been treating the unexplored deep as a failure, as something we neglected, a blank we should have filled and didn't. But descend through that pressure, and cold, and dark, and neglect stops being the right word. We haven't failed to explore the deep out of disinterest. We've been held out of it by physics. The deep ocean is one of the most genuinely hostile environments this planet has, harder to operate in some ways than the surface of the moon. Because on the moon, nothing is trying to crush you flat. The reason we've seen so little isn't that we didn't try. It's that the place actively resists being seen, with three of the most punishing physical forces we know layered on top of each other, kilometers thick. And notice the twist hiding in that. The same wall that keeps us out has been doing something else the entire time. It's been protecting what's down there, because almost nothing can operate in that environment, including us. The deep sea has stayed one of the least disturbed places on Earth. That darkness and pressure that block our cameras also blocked almost everything else. So the deep isn't a wasteland behind the wall. It's more like a vault. The very hostility that hid it from us also kept it intact, slow, ancient, undisturbed. In a way almost nowhere on the surface still is. The barrier isn't just the reason we haven't seen it. It's part of the reason there's something so untouched left to see. But here's the thing I have to admit now, because it changes the scale of the whole problem. Everything I just described, the pressure, the cold, the dark, the crushing wall, all of that has been about reaching the floor, getting a vehicle down to the bottom and looking at the ground. And this entire video so far has quietly been about the floor. The map is a map of the floor. The Rhode Island patch is a patch of floor. The 27%, the gravity outline, the biased sample, all of it, the bottom. But the ocean isn't a floor. The floor is just the very bottom of it. Above that floor stands the water itself, kilometers of it, a towering column reaching from the bottom all the way up to the surface. And that water isn't empty space you pass through on the way down. It's alive. It's the largest living space on the entire planet, vastly bigger than the floor beneath it. And it's inhabited from top to bottom by things built for the dark and the pressure. When we talk about how little of the ocean we've explored, we've been arguing about a two-dimensional surface, the bottom, while ignoring the enormous three-dimensional volume standing over it. And that volume is even less understood than the floor. At least the floor holds still long enough to map. The water column is a moving three-dimensional wilderness that you can't chart the way you chart terrain, full of animals that never touch the bottom and never come to the surface, living their entire lives suspended in the black middle of the sea. We've been measuring our ignorance of the seafloor and calling it our ignorance of the ocean. They are not the same. One is a surface. The other is a volume so large it makes the whole seafloor debate look like we were arguing about the doormat while ignoring the house. So the real unexplored ocean isn't the floor at all. It's the space above it. And that space plays by rules even stranger than the ones down here in the crushing dark. Everything up to now has been about the floor. The map is the floor. The Rhode Island patch is the floor. Every number I've thrown at you measures the bottom of the sea. And that means every number so far has been quietly answering the wrong question. Or at least a much smaller question than the one the title asks. Because the ocean is not a floor. The floor is the last thin layer at the very bottom of it. Standing above that floor is the thing we've been ignoring this whole time, the water itself. Here's the mistake almost everyone makes, and I made it too, for the first 8 chapters on purpose. We picture the ocean as a surface with a bottom, a skin of water on top, a floor down below, and the ocean is basically the floor, the place with the terrain, the mountains, the trenches, the ground you can map. So, how much of the ocean have we explored collapses into how much of the seafloor have we seen? That's the unspoken assumption behind the whole debate, behind the 5% myth, behind the map on the wall. Explore the ocean, we think, means chart the bottom. Break that assumption, and the problem doesn't just change. It explodes. Because between the surface and the floor stands the water column, kilometers of open ocean, top to bottom, filling the space we've been treating as empty transit. When an ROV sinks for hours through the black on its way to the bottom, it isn't crossing nothing. It's passing through the largest living space on the entire planet. Not the largest in the ocean, on the planet. More habitable volume than every forest, desert, grassland, and mountain range on land combined, many times over. And it's not a corridor you pass through to get to the interesting part. It is the interesting part. The floor is the doormat. The water column is the house, and the house is enormous, and it's full. Think about the geometry of that for a second, because it reframes every figure in this video. The seafloor is a surface, a two-dimensional sheet, however wrinkled. You can measure it in square kilometers, shade it in on a map, talk about what percentage is covered. But the water column is a volume. It has height, kilometers of it, stacked on top of every one of those square kilometers. So whatever fraction of the floor we've seen, the fraction of the ocean's living volume we've seen is dramatically smaller. Because for every patch of bottom, there's a towering column of inhabited water above it that we've observed even less of. Our tiny Rhode Island patch was a patch of floor. The volume of open ocean we've actually explored is a far thinner sliver of a far larger thing. We didn't just underestimate how little of the ocean we've seen. We measured the wrong dimension and made ourselves look better than we are. And this volume isn't sparsely populated wilderness you'd have to hunt to find life in. It's the opposite. The open water of the deep, the midwater, the vast, dark middle of the sea between the sunlit top and the distant floor, is where an enormous share of the planet's animal life actually lives. Creatures that are born in that suspended blackness live their whole lives there and die there, never once touching the bottom, never once rising to the light, an entire biosphere hanging in the dark, in 3 dimensions, with no floor and no ceiling that matters to it. We built our whole sense of exploring the ocean around the ground, and the ground is where a lot of these animals never go. Here's the piece that should genuinely reset how big you think this is. That midwater life performs a movement every single day that is by sheer mass one of the largest migrations on Earth. And it happens vertically, in the dark, mostly out of sight. As the sun sets at the surface, vast populations of small animals that spent the day hiding in the deeper, darker water rise upward toward the surface to feed under cover of night. Then, before dawn, they sink back down into the dark to hide from the predators that hunt by light. Up every night, down every morning. A tidal wave of living things moving through the vertical, planet-wide, every day, on a scale that dwarfs any migration you can watch on land. And it plays out in the one part of the ocean we've been treating as empty space to fall through. We know this migration happens. And here's the unsettling part. A lot of what we know about it, we didn't learn by looking. We learned it by accident, from sound. Early sonar operators kept detecting a strange layer in the open water, something that reflected their pulses back as if there were a false bottom suspended in the middle of the sea. A floor that wasn't a floor, that rose and fell with the light. It took time to understand they were bouncing sound off the migration itself, off the sheer density of living things moving up and down. We detected the largest daily movement of life on the planet as a ghost on a sonar screen before we understood what it was. That's how little we were watching the water column. We found one of Earth's great biological events by mistake, in the echoes. Now put that against the maps. You cannot map a volume the way you map a floor. A seafloor map is a picture of a surface. Here's the terrain, shade it in, move on. But how do you draw a map of a 3-dimensional wilderness that's kilometers deep, has no fixed features to chart, is full of animals that move through it in every direction, and rearranges itself every single day as its inhabitants rise and fall? The whole concept of mapping barely applies. There's no terrain to trace. The thing you'd be mapping is the water itself and the life suspended in it, and both are in constant motion. Most of the ocean's living volume doesn't just lack a map. It can't be captured by the kind of map we've been arguing about for 8 chapters. We've been debating the resolution of a picture of the floor while the largest part of the ocean sits in a form no floor map could ever represent. So the honest scope of unexplored just grew by an order of magnitude, maybe more. It's not that we've seen 0.001% of the seafloor and the rest is roughly similar. It's that even the seafloor question, as hard as it is, was the smaller question. Standing above every unmapped patch of bottom is a column of living water we understand even less, that holds more life than the floor, that stages one of the planet's biggest daily events out of our sight, and that resists the very idea of mapping. When people say we've explored a few % of the ocean, they're not just wrong about the number. They're picturing the ocean as a floor with some water on top, when the truth is the reverse. It's a vast living volume with a floor at the bottom, and the volume is the part we've barely touched. Which finally lets me deal with the comparison you've probably been waiting for this entire video. The line everyone reaches for when they want to make the ocean sound unexplored. We know more about the surface of Mars, they say, or the moon, than we do about our own ocean. You've heard it 100 times. And it's the perfect thing to test right now because we've just spent 9 chapters building the tools to actually judge it. Is it true? Is it nonsense? Or is it one of those lines that's sloppy and misleading and somehow underneath, still pointing at something real? The answer is more interesting than a yes or a no. And it hinges on exactly the thing we've been circling. The difference between mapping a surface and actually seeing a world. We know more about the surface of Mars than we do about our own ocean floor. You've heard that line 100 times. In documentaries, in articles, probably in the back of your own head every time the ocean comes up. It's the go-to proof that the sea is a mystery. And after 9 chapters, you finally have the tools to put it on trial. So, let's do that. Is it true, or is it the same kind of lazy, repeated non-fact as the 5% we started with? The honest answer is, it's both. It's sloppy, it's misused, and underneath the sloppiness, it's pointing at something real, which makes it the perfect thing to examine because pulling it apart shows you exactly what explored has meant this whole time. Start with the version that's true because there's a real one in there. If you mean mapped, the shape of the terrain, the resolution of the picture, then for a long time, yes, we genuinely had sharper maps of Mars and the Moon than of most of our own seafloor. And the reason is the thing we've been fighting since Chapter 3, water. Mars has no ocean hiding its surface. The Moon has no ocean, no atmosphere worth mentioning, nothing in the way. So you can put a spacecraft in orbit, point instruments straight down, and map the ground directly. Light, radar, laser altimeters, cameras, all reaching the surface unobstructed. You can image another world's terrain from orbit in detail that for large stretches of it beat what we had for the bottom of our own sea. Now compare that to the seafloor. You cannot point a camera from orbit and photograph the bottom of the ocean because kilometers of water sit in the way and swallow everything. Light can't reach it. Radar can't reach it. The one thing we could do from orbit, read the gravity bumps at the surface, gave us that blurred 12 to 16 kilometer map where a 2-kilometer mountain can vanish. So for the seafloor, the best global view we had was the smudge, while for Mars we had the actual ground. Put those side by side at matched scale, and the Martian tiles genuinely looked sharper than the ocean floor tiles. The line wasn't invented. It came from a real gap, and the gap was carved by the simple, brutal fact that water blocks what vacuum lets through. So the cliché earned some respect. There was a stretch of history where, by the measure of map resolution, we really did have a clearer picture of another planet's surface than of the floor of our own ocean. That's not nothing. That's a genuinely strange fact about where our knowledge went. But, and this is where the line starts lying, that comparison is quietly cheating in 2 directions at once. Here's the first cheat. We know more about Mars compares a map to a map, resolution to resolution. And by now you know that mapping is the shallowest meaning of explored. We have a map of Mars, sure, but have humans, or our machines, ever actually gone to most of that Martian ground and looked at it up close, sampled it, watched what happens there? Barely. A handful of rovers on a few tiny tracks, a few landing sites, enormous stretches never touched. Mars is well mapped and almost entirely unvisited, which, if you think about it, is exactly the situation we found for our own seafloor. Mapped from a distance, seen up close almost nowhere. So the comparison, made honestly, doesn't say Mars is explored and the ocean isn't. It says both are mapped and neither is really seen. the line takes the one dimension where Mars wins, map sharpness, and quietly implies Mars wins on all of them. It doesn't. And the second cheat is the bigger one, and it's the thing the last chapter set up. The comparison is about surfaces. Map of the Martian surface versus map of the ocean's surface, meaning its floor. But the ocean isn't a surface. It's that towering, living, three-dimensional volume we just spent a whole chapter on. Mars is, for this purpose, a two-dimensional world. A ball with a surface and essentially nothing living above it to explore. The ocean is a volume packed with life from top to bottom. So even if we knew the Martian surface perfectly, comparing it to the ocean floor compares a complete thing to the bottom slice of a vastly larger thing. It's not that we know Mars better than the ocean. It's that Mars is a surface and the ocean is a volume, and you can't put a percentage on one that means the same as a percentage on the other. The line smuggles in the assumption that the ocean is a floor, the exact assumption we just spent a chapter destroying. So here's the verdict, and it's more useful than a simple true or false. The more than Mars line is right about the narrow thing and wrong about the big thing. Right that for a long time our maps of another world's surface were sharper than our maps of the seafloor, because water is a wall that vacuum isn't. Wrong in the impression it leaves, which is that Mars is a known place, and the ocean is the mystery. The truth is that both are mapped but unseen, and the ocean has an entire extra dimension of living volume that has no equivalent on Mars at all. The line makes the ocean sound like it's losing a fair race. It isn't a fair race. It's two different kinds of thing, and the ocean is the far larger, far more alive, far harder one. And there's a final turn that makes even the narrow, true version of the line start to expire. Remember what happened when that newer satellite came online at the end of 2022. The one that measures the sea surface in wide swaths and sharpened the gravity map from 16 kilometers down to around 8. The moment we got a better instrument, the seafloor map got dramatically sharper, and tens of thousands of hidden seamounts appeared. That closing the gap is still happening. The very reason More Than Mars was ever true, that our seafloor maps were coarse, is being actively erased year by year as the tools improve. The line describes a gap that's shrinking under our feet even as people repeat it. Say it today, and you're quoting a fact with an expiration date, one that was carved by the difficulty of seeing through water, and is being filed down by every better satellite we launch. So the famous comparison turns out to be exactly like the 5% number we opened with, repeated everywhere, treated as a clean fact, and actually a blur. Technically rooted in something real, but misused to say far more than it can support. Both of them are people reaching for a simple number to express a true feeling, that the ocean is staggeringly unknown, and both of them getting the mechanism wrong. The ocean is staggeringly unknown. Not because it loses a map resolution contest to Mars, because it's a crushing, dark, kilometers-deep living volume that we've physically seen almost none of, which raises the question that all of this has been quietly building toward. If we've seen so little, a sliver of the floor, almost none of the volume, a biased scrap of the whole, then what actually happens on the rare occasions when we do go and look? When a vehicle does descend into an unwatched patch of the deep and switches on its lights, what does it find? Empty mud, confirming that the darkness is mostly barren? Or something else? Because the answer to that is the strongest evidence in this entire video for how much is still out there. Every time we genuinely look, the deep does the same thing. And what it does should tell you exactly how far from finished we really are. So we've seen almost none of it. A sliver of the floor, a scrap of the volume, and the little we've watched is crowded into a few countries' waters. Which leaves one question that cuts straight to the point. When we do go, When a vehicle drops into some unwatched patch of the deep and switches on its lights? What's actually there? Empty mud, proving the dark is mostly barren? Or something that tells us the emptiness was never real, just unwatched? The answer is consistent enough to be unnerving. Almost every time we genuinely look at a piece of the deep we haven't looked at before, we find something new. Not occasionally, not on the lucky expeditions. As a rule, looking in the deep sea is nearly the same thing as discovering, and that single fact is the strongest evidence in this entire video for how much is still out there. Break the assumption first because it's a natural one. You'd expect new discoveries to be rare events. The payoff of 100 boring dives. A needle you occasionally hit after endless empty haystacks. That's how discovery usually feels on land, where the easy finds were made long ago, and each new one takes more digging. The deep sea runs the opposite way. The finds aren't the exception. They're the baseline. Send cameras somewhere genuinely unobserved, and the question isn't whether you'll see something science hasn't cataloged. It's how many. Modern deep-sea expeditions routinely come back having spotted animals that appear to be entirely new to science. Creatures no one has named, sometimes dozens of candidate new species from a single campaign. Occasionally more than 100 from one stretch of exploration in a barely studied region. Sit with what that implies. If you can drop into an underexplored patch of deep ocean and, in a matter of weeks, film that many things that might be new, then the deep isn't a mostly known place with a few gaps left. It's the reverse. A mostly unknown place where the known things are the exceptions. The rate of discovery is a measurement in itself. And what it measures is how empty the catalog still is. Here's the reversal. That turns this from a fun fact into something heavier. When you're near the end of exploring something, the discovery rate falls. You've found the common things, then the rare things, and each new trip turns up less, until finally you're mostly confirming what you already knew. That's what almost finished looks like. Diminishing returns. The deep sea shows no sign of that. The discoveries aren't slowing down. Every well-run expedition into new territory keeps hitting new life, at a pace that hasn't collapsed the way it would if we were closing in on the full picture. And a discovery rate that isn't falling tells you something blunt. We are nowhere near the end. You don't get a steady stream of the never-before-seen from a place you've nearly finished exploring. You get it from a place you've barely started. And it's not only the animals. Remember the mountains. When that Sharper satellite came online and the seafloor map jumped from 16 kilometers of resolution down to 8, tens of thousands of seamounts appeared that we hadn't known were there. The estimate of how many seamounts dot the world's oceans, potentially climbing from around 44,000 toward 100,000. Think about what those mountains are in this context. Each seamount is a feature that rises off the floor into the water column, and seamounts tend to be oases. Places where deep currents hit the slopes, where life concentrates, where whole communities gather that don't exist on the flat plains around them. So we didn't just find more terrain. We found tens of thousands of the exact features most likely to be teeming with life. And we found them by improving a satellite, not by visiting a single one, which means there are right now tens of thousands of underwater mountains, each potentially its own gathering of deep-sea life that no one has ever seen. We know they exist. We know they're probably rich, and we have looked at almost none of them. Put those two things together, and the scale of what's unexplored stops being an abstraction. It's not just blank space on a map. It's tens of thousands of known, unvisited mountains, each likely to be an oasis of life, sitting inside a volume of water that keeps producing new species every time we point a camera at it. The unexplored deep isn't a void we've been imagining as empty. It's crowded. That's the twist that should stay with you. All this time, unexplored has carried a quiet flavor of empty, as if the reason we haven't seen it is that there's not much to see. Every piece of evidence points the other way. The places we haven't looked aren't barren. They're full, and full of things we've never encountered, and the only reason we call them unknown is that we haven't shown up yet. And this reframes the tiny numbers from earlier in a way that makes them heavier, not lighter. Less than 0.1% of the deep sea floor seen. But the fraction we did see was dense with the new. If a sample that small, that biased, that crowded into a few regions still keeps turning up unfamiliar life, then the reasonable expectation for the unwatched 99.99+% isn't probably similar and mostly known. It's probably full of things we cannot currently imagine in quantities we can't estimate. We can't estimate because every time we sample it, we're surprised. The smallness of what we've seen and the richness of what we found in it aren't two separate facts. Together, they're an argument. They say the deep is not just unexplored, but underestimated. That the real inventory of life down there is something we've barely begun to guess at. There's a reason the deep keeps surprising us. And it's the same wall from before, wearing a different face. The deep sea is a set of conditions so different from the sunlit world. The permanent dark, the crushing pressure, the cold, the scarcity of food. That life there has been solving problems we don't even have. And it solved them in forms we didn't predict, because we design our expectations around the world we know. When you look somewhere, the rules are that different. The solutions life came up with are that unfamiliar. That's why looking equals discovering. It's not luck. It's that we're peering into a portion of the planet running on a different rule book, and every glimpse of the rule book shows us a page we hadn't read. So here's where all of this lands, and it's about to turn from wonder to something more uncomfortable. We've established that the deep is vast, unseen, and, every time we check, full. Full of unknown life dotted with tens of thousands of unvisited mountains, running on biology we barely understand. A place we've observed a sliver of and been surprised by nearly all of. And that's exactly the place we're now preparing to reach into and use. Because at this very moment, decisions are being made, real ones, with real consequences, about extracting things from the deep sea, mining it, storing things in it, drawing lines across it, and granting rights to it. Decisions that could reshape the largest habitat on the planet. And they're being made about a place we've seen less than 0.1% of, using a picture we've just spent 11 chapters proving is almost entirely blank. We might start rewriting the deep ocean before we've ever really looked at it. And that turns this from a story about wonder into a story about stakes. Everything until now has been about wonder. How much is out there? How little we've seen. How strange the real numbers are. This is where it stops being only wonder and starts being a problem with consequences. Because the deep ocean we've spent 11 chapters proving is almost entirely unseen is, right now, being lined up for use. Not studied, used. And the gap between how little we know and what we're preparing to do with it is where this whole story turns sharp. Here's the uncomfortable setup. We've established that we've visually seen less than 0.1% of the deep sea floor. That the little we've seen is crowded into a few nations' waters. That the water column above it is barely touched. That every time we look, we find things we didn't know existed. So our picture of the deep is not just incomplete, it's a scrap, a biased scrap, surrounded by blankness we know is full, but haven't examined. That's the state of our knowledge. Now hold that next to the decisions being made on top of it. There is serious, active pressure to mine the deep sea. The floor and parts of the deep is scattered with mineral deposits, metal-rich nodules lying on the abyssal plains, mineral crusts on seamounts, deposits around hydrothermal systems, containing metals the surface world wants badly. And so there are plans and claims and international negotiations about going down to those abyssal plains and harvesting them at industrial scale. Machines on the seafloor, kilometers down, stripping nodules off the bottom across enormous areas. The economic logic is real. The metals are real. And the places being eyed are, in many cases, exactly the kind of deep, remote, barely observed bottom that sits in the 99.99+% nobody has ever looked at. Now put the two facts in the same sentence and feel how wrong it sits. We are preparing to industrially alter parts of the deep seafloor that we have never seen. Not seen a little. Never. There are regions under serious consideration for mining where the visual record is essentially nothing, where our entire knowledge of what lives there, how it's structured, what depends on it, comes from that biased sliver and a blurred map. We'd be sending machines to reshape a place before anyone has laid eyes on it, building on ground we never surveyed, rewriting a page we never read. And the thing that makes this genuinely serious rather than just poetic is the nature of those nodules. The metal-rich nodules on the abyssal plains take an almost unimaginable amount of time to form. They grow at a pace measured over millions of years, accreting layer by microscopic layer across spans that dwarf human history. Whatever life has organized itself around them has done so over that same immensity of time. So this isn't like harvesting a crop that grows back. On any time scale that means anything to us, what gets removed is gone. The consequence is effectively permanent. We would be making an irreversible change to the largest, least understood habitat on Earth, in places we've never observed, based on a picture we've spent this whole video proving is nearly blank. Here's the reversal that ties it back to everything before. All along, our ignorance of the deep has felt like a source of wonder, the thrill of an unexplored frontier, the excitement of not knowing. The same ignorance pointed at these decisions stops being thrilling and becomes dangerous. The exact blankness that makes the deep exciting to explore is what makes it perilous to exploit, because you cannot weigh what you'd be destroying if you've never seen it. You cannot judge whether a species matters, or is rare, or exists nowhere else when you haven't yet discovered it. And we know, from the relentless drumbeat of new life every time we look, that undiscovered species are almost certainly there, in the very places being considered. To mine those regions now is to risk erasing things we haven't met yet. Not hypothetically, given the discovery rate, near certainly. And it isn't only mining. The deep is being drawn into other decisions of the same shape. There's growing interest in using the ocean, including its depths, to store carbon, to lock away the excess we've pumped into the atmosphere by moving it into the deep sea in one form or another. The instinct is understandable. The deep is vast and cold and slow, and it already holds enormous amounts of carbon naturally. But it's the same problem wearing a hopeful face. We'd be deliberately altering the chemistry or the load of a system we barely understand, whose workings we've observed a sliver of, whose responses we can't fully predict, because we've never watched it closely enough to know how it behaves. Good intentions don't fix the core issue. You're still acting on a place you haven't seen. Underneath all of it runs the same structural problem, and it's worth naming plainly. Good decisions need good information. When a government decides how to manage a forest or a fishery near the coast, there's at least a real body of observation underneath, surveys, counts, decades of watching. The deep sea offers almost none of that. The decisions about mining it, storing things in it, drawing rights across it, are being made on top of the thinnest evidence base of any environment on the planet, a fraction of a percent, skewed toward a few regions, blind to the volume above the floor. We are being asked to make possibly permanent choices about the largest habitat on Earth, using less direct knowledge than we have about almost anywhere else. That's not a knock on the people making the decisions. It's the situation they're stuck in. You cannot survey your way to certainty fast enough when the place resists being seen this hard, and the pressure to act is already here. So the tiny numbers from the earlier chapters change, meaning one more time. Back then, less than 0.001% seen was a fact about wonder. Look how much mystery is left. Now it's a fact about risk. Look how little we know about a place we're about to change. The same number, a completely different weight. And that's the shift this chapter is really about. The unexplored deep isn't just an adventure waiting to happen. It's a decision waiting to be made. And we're moving toward making it while the map is still nearly empty. We might rewrite the deep ocean before we've read it. There's one more place this has to go because so far even this has been about the reachable deep. The abyssal plains, the nodule fields, the parts we could plausibly send machines to today. But the ocean doesn't stop there. Below the abyssal plains, in a handful of places, the seafloor plunges further still. Into the trenches, the Hadal Zone, the deepest water on the planet, where the pressure climbs past 1,000 atmospheres and even our best machines have gone only a handful of times. If the abyssal plains are barely seen, the trenches are barely reached at all. And what explored means down there, at the absolute bottom of the world, is smaller and stranger than anywhere we've been yet. Everything so far has been about the reachable deep, the abyssal plains, the nodule fields, the wide flat bottom that sits a few kilometers down. But that's not the bottom of the ocean. In a handful of places, the seafloor doesn't just lie there kilometers down. It drops further, tiers open into long, narrow gashes that plunge past the abyssal plains into the deepest water on the planet, the trenches, the Hadal Zone. And if the abyssal plains are barely seen, the trenches are barely reached at all. This is the floor of the floor, and what explored means down here is smaller than anywhere we've been yet. Break the assumption right away, because this is the one place people are sure has been conquered. You've heard that humans reach the bottom of the deepest trench. It's true. People have descended to the very deepest point in the ocean, to the floor of the Mariana Trench, nearly 11 kilometers down. It's held up as a finish line. We went to the deepest place, therefore the deep is done, checked off, mastered. And that framing is exactly the trap this whole video has been about. Reaching a point is not exploring a zone. Someone standing on a single spot at the bottom of the deepest trench has explored the Hadal Zone about as much as one person parachuting onto one hilltop has explored an entire mountain range they can't see the edges of. Because the Hadal Zone isn't a point. It's a scattered system of the deepest trenches around the world. Long, deep trenches, mostly rimming the Pacific, where the plates dive under one another, plus a handful elsewhere. Added together, they're a real and distinctive slice of the planet, an entire category of environment. And the total number of times humans have physically descended into the very deepest of them is not in the thousands or the hundreds. It's a scattering. A handful of crude dives to the extreme deep across the whole history of exploration, plus a modest number of unmanned landers and instruments dropped down and hauled back. Against the size of the Hadal system, that's not exploration. That's a few pinpricks in an enormous dark. Make the comparison that lands hardest. The deepest points of the ocean have been visited by fewer people than have walked on the surface of the moon. Think about that. The bottom of our own ocean, the deepest ground on our own planet, closer to you right now than most of the places on Earth you'll never go, has felt fewer human visitors than another world 250,000 miles away. Not because it's farther, because it's harder. The wall of dark and cold and pressure reaches its absolute maximum here, and it turns the deepest trenches into some of the least visited real estate accessible to our species anywhere, on or off the planet. The reason is the pressure, taken to its furthest extreme. Remember the rule. Every 10 meters down adds another atmosphere. Run that rule to the bottom of the deepest trench, nearly 11 kilometers, and you arrive at more than 1,000 atmospheres. Over 1,000 times the pressure you live under. Force enough to collapse almost anything not engineered specifically to survive it. To send a crewed vehicle down there is to build a machine that can hold back the weight of the entire ocean column and keep a human alive inside it, in the cold and the black, at the bottom of the world, and bring them home. The number of vehicles ever built that can do it, across all of history, you could count without much trouble. This is the sharpest end of the affordability and physics wall. So few can reach it that the deepest zone stays almost by definition unexplored. And here's the reversal that makes the trenches more than just a record for deepest. You might assume the very bottom, the most extreme, most crushing point, is where life finally gives up. That below a certain depth, it's just sterile mud under impossible pressure. Nothing left to find. Nothing worth reaching for. The opposite is true. Life persists all the way down. Even at the bottom of the deepest trenches, under more than 1,000 atmospheres, in permanent freezing dark, there are organisms living, animals built for a world that would destroy almost everything else. Some of them found nowhere but in these deep gashes. The trenches aren't dead ends. They're isolated worlds, cut off from each other by the abyssal plains between them, each one a deep, separate pocket where life has been solving the harshest version of the deep sea problem in its own way. And we've visited a scattering of them a scattering of times, which means the Hadal Zone stacks every problem in this video into one place at maximum intensity. It's the least mapped. Trenches are narrow and deep, and hard for even sharp sonar to fully capture. It's the least seen. A few descents against an entire category of environment. It's the least sampled. Reaching down to grab something from the bottom of a trench is a feat in itself, and it's inhabited by life we've barely met, isolated in pockets we've barely entered. Every measure of unexplored we've built across this whole story hits its extreme at the bottom of the trenches. If the deep sea is the least known place on the planet, the Hadal Zone is the least known place in the least known place. The unexplored ocean has a floor, and that floor is the most unexplored ground there is. And notice what that does to the triumphant story. We reach the bottom. It's real, and it's an extraordinary feat of engineering and nerve, and it's also a single dot. Our proudest deep-sea firsts, the ones held up as proof we've conquered the depths, are exactly that. Firsts, single points. A person at the deepest spot, a vehicle at the bottom of one trench, magnificent, and almost meaningless as coverage. Reaching the deepest point told us we could get there. It told us almost nothing about the vast Hadal system stretching away in the dark on either side, unvisited. The finish line framing gets it backwards. Those dives weren't the end of exploring the deep. They were proof of how little a single visit covers. The same lesson as the crawling ROV light, written at the very bottom of the world. So here we are, at the deepest ground on the planet, and the picture is the bleakest version of everything we found. Barely mapped, barely reached, barely sampled, and alive with things we've hardly seen. The ultimate expression of an ocean we've been fooling ourselves about for this entire story. It would be easy to end there. On the wall, on the dark, on how little we've done and how much resists us. But that's not actually where this ends, because something is changing. Right now, in the last few years, that starts to crack the wall we've spent this whole video building up. The reasons we've seen so little were never really about willingness. They were about cost and reach and the sheer punishing difficulty of getting eyes into the deep. And every one of those barriers is, for the first time, starting to give. It would be easy to end on the wall, on the dark, the pressure, The trenches nobody reaches, the map that's mostly blank. That's the honest shape of everything so far. A place that resists being seen, and a species that's barely managed to see it. But that's not where this ends, because in the last few years, something has started to crack. The barriers that kept us out of the deep were never really about willingness. They were about cost and reach and the brutal difficulty of getting eyes to the bottom. And for the first time, every one of those barriers is starting to give. Start with the shift that matters most, because it changes the whole nature of the problem. For most of this story, the wall around the deep was a wall of possibility. The deep was hard to reach because we barely had machines that could survive it at all. A crewed vehicle that can hold back 1,000 atmospheres is a rare, monstrously expensive thing. If exploring the deep means building more of those, we'll never cover much because you can only make so many, and each one can only be in one place. That's the world that produced a Rhode Island-sized patch in 70 years. But the bottleneck has quietly changed shape. It's shifting from impossible to merely expensive. And expensive is a problem you can attack. The thing that resets the math is autonomy. You don't actually need a person at the bottom to look at the bottom. You need eyes, lights, and something to carry them. And once you remove the human, the life support, the safety margins, the crude sphere thick enough to keep someone alive, you remove most of what made deep exploration so scarce. A robot doesn't need to come back alive in the same way a person does. It doesn't need the ship holding station overhead for hours, tethered by a cable kilometers long. Cut the human and the tether, and the whole economics of looking at the deep starts to come apart in the best way. That's the real promise of the machines now coming into the water. Autonomous vehicles that descend on their own, roam the seafloor without a cable to a mothership, do their work in the dark, and come back up when they're done. No tether, no ship pinned in place above them, burning money by the hour, and crucially, not one at a time. Once a vehicle doesn't need a dedicated crewed ship babysitting it, you can imagine many of them, fleets, swarms, dozens of cheaper robots spreading out across the dark instead of a single priceless vehicle inching along one strip. The whole reason coverage was so small was that we could only ever look in one narrow place at once. Break that, and the arithmetic of exploration changes for the first time since it began. And the reach problem, the same one, is being attacked from the mapping side too. Remember the ship dragging its sonar fan, one strip at a time, at the pace of a bicycle, which got us to only about a quarter of the floor after decades. Autonomous and uncrewed surface vessels can now run those sounders without a full crew aboard, crossing ocean on their own, filling in strips far more cheaply than a fully staffed research ship. Add the crowdsourcing, commercial ships, fishing vessels, any boat willing to run its sounder and donate the data as it crosses water no survey ship would ever be sent to. The map that was creeping upward strip by expensive strip now has cheaper hands filling it in. And overhead, the satellite side keeps sharpening. That jump from 16 kilometers of resolution to 8, from 1 year of a better instrument, with more years of data still to process. The blurred gravity map is getting less blurred even as the ships and robots work from below. There's another force here, quieter, that multiplies all of it. We are drowning in more deep-sea imagery than anyone can watch. Every ROV dive, every autonomous run, produces hours upon hours of footage of the dark, and there simply aren't enough trained human eyes to review it all. Vast amounts of deep-sea video have been recorded and never fully examined, because watching it is slow, expensive human labor. Now put pattern recognition software on that pile, systems that can scan through footage and flag the animals, sort the life from the empty mud, count and identify at a speed no human team could match. Suddenly, the bottleneck isn't just getting the eyes down there, es nos mandem babansim wane. It's that we couldn't process what the eyes already sent back, and that logjam is starting to clear too. We may find that some of the deep was already seen, sitting in unwatched archives, waiting for something that could finally look through it all. Here's the twist worth pausing on, because it inverts the whole heroic image of deep exploration. For a century, the story of the deep was a story of going deeper. The race to the bottom, the crude descent to the deepest trench, the triumph of putting a human at the lowest point on Earth. That was the dream. Deeper, braver, further down. But the thing that might actually close the gap isn't going deeper. It's going wider and cheaper. Not one heroic vehicle at the absolute bottom, but many humble ones spread across the dark. The future of seeing the ocean probably doesn't look like a person in a sphere at the deepest point. It looks like a swarm of cheap robots quietly filming ordinary abyssal plane, and software sorting the footage while everyone sleeps. Cheap eyes everywhere may matter far more than one brave descent to the very bottom. The wall doesn't get broken by a stronger hammer. It gets dissolved by making looking ordinary. Be honest about the limits, though, because this isn't solved. It's becoming solvable, which is a different thing. The ocean is still enormous. Even swarms of cheap robots against 2/3 of the planet, in 3 dimensions, is a staggering amount of water. The global effort to finish mapping the whole floor in sharp detail by the end of this decade is a real goal with real momentum, but it's a goal, not a certainty. And it's only the map, the shape, not the seeing. Closing the gap between mapped and seen, between the floor and the volume, is a vastly bigger task that no deadline covers. The barriers are giving. They are not gone. What's changed is the direction of the trend. For most of history, the deep was getting explored so slowly, the number barely moved. And now, for the first time, the tools exist to make it move. So the story finally turns. Not to a clean victory, there isn't one, not yet, but to a genuine shift. The reason we'd seen almost none of the ocean was never that it wasn't worth seeing, or that we didn't want to. It was that looking was too hard and too expensive to do at scale. That specific wall, the one this whole video has been built on, is the thing that's cracking. Which means the almost total blankness we've spent 13 chapters staring into might be less a permanent condition than a snapshot of a particular moment. The moment right before the tools caught up. Which brings us back to the question we started with. The one buried inside a 5% number that turned out to be a lie in every direction. After all of it, the blurred map, the sharp quarter, the sliver we've seen, the volume we've ignored, the trenches, the swarms, coming to change it. How much of the ocean have we actually explored? It's time to put the honest number together, and it's nothing like the one you were handed. So, after all of it, how much of the ocean have we actually explored? You came in with a number, 5%, clean, confident, repeated, everywhere. And we've spent 14 chapters proving that number is a lie in every direction it could be a lie. Now it's time to put the honest answer in its place. Not a single number, 3 of them. Because that was the whole trick from the beginning. The lie was pretending one number could answer a question that was always 3 questions wearing the same coat. Bring back the bars from the very start. 4 of them, standing at wildly different heights, one word blurred across all of them. Let's finally fill them in with what we found. The first bar, mapped. In the loosest sense. Do we have any map of the shape of the bottom? That bar goes all the way up. 100%. There is a complete map of the entire ocean floor. And you've seen it. And it's real. But we know now what that map actually is. A blurred sketch read from bumps in the sea surface. Gravity's shadow of the terrain. Sharp enough to show a mountain range and too coarse to catch a 2-kilometer peak sitting right there in the blue. A full map, yes. A full map made of inference. where a feature the size of a city can hide in the smoothness. The floor was never seen to make it. It was deduced from above. The second bar, mapped in real detail. The sharp map, dragged up from below by ships, one strip at a time. That bar stands at about 27%, roughly a quarter of the seafloor charted properly, in genuine resolution. And even that took the biggest coordinated mapping effort in human history, running for years, filling in partly by accident from ships crossing on their way to somewhere else. A quarter, in focus. 3/4 still just the blur. And the third bar, seen, actually looked at. A camera, an eye, real light on the real ground. That bar is so short it almost doesn't clear the axis. Less than 1,000% of the deep sea floor ever observed. A patch the size of one small state against a deep sea covering 2/3 of the planet. 70 years, 43,000 dives, every deep-diving nation there's ever been. And the sum of all that looking is a scrap you could cross in an afternoon. And a scrap crowded into a few wealthy countries' waters, blind to whole basins the size of continents. 3 bars, all the way up, a quarter of the way up, and a whisper above zero. That is the honest answer. And now you can see exactly why the 5% number was a lie in both directions at once. If you meant the map, 5% was absurdly too low. The real figure is everything. If you meant what we've truly seen, 5% was wildly too high. The real figure is thousands of times smaller. 5% was never right for any definition. It sat in the middle, a compromise between two truths it belonged to neither of, and it survived precisely because it was vague enough to never quite be wrong out loud. The map on the classroom wall was a guess dressed as knowledge. The number under it was a blur dressed as a fact. But here's the thing the 3 bars still don't capture, and it's the part that should stay with you longest. Every one of those bars measures the floor, the shape of the bottom, the detail of the bottom, the seeing of the bottom. And the ocean was never a floor. Standing above every square kilometer of that seafloor is a column of living water kilometers deep. The largest habitat on the planet, a 3-dimensional wilderness that stages one of Earth's biggest daily migrations in the dark, that we found by accident as a ghost on a sonar screen, that no floor map could ever represent. So even the third bar, the tiny one, is measuring the wrong dimension. The real fraction of the living ocean we've seen is smaller than the smallest bar, because for every scrap of floor we've watched, the towering volume above it went unwatched too. We've been arguing about the doormat. The house is still dark. And this is where the reframe lands. The shift from where you started to where you are now. You came in thinking the ocean was mostly unexplored because it had been neglected, because nobody bothered, because it was somehow a blank we forgot to fill. That's the feeling the 5% number leaves you with, a vague sense that we could have looked and didn't. Everything we've walked through says the opposite. We didn't fail to look out of disinterest. We were held out by a wall. The dark that swallows light in 200 meters. The pressure that stacks a sky every 10. The cold, the sheer punishing cost of getting a single eye to the bottom and back. The ocean isn't unexplored because we forgot it. It's unexplored because looking is the hard part, the expensive part, the part that resists us more than almost anywhere else on or off this planet. The blankness on the map isn't the shape of our neglect. It's the shape of how fiercely the deep defends itself from being seen. And that same wall that kept us out kept the deep intact. The darkness that blocked our cameras blocked almost everything else. So what's down there isn't a picked-over wasteland. It's a vault. Slow, ancient, undisturbed. And every time we crack it open even slightly, it's full. Full of life we've never named. Dotted with tens of thousands of mountains no one has ever visited. Running on biology, built for a rule book we're only beginning to read. The unexplored ocean was never empty. It was just unwatched. And that changes what the blankness means. It's not a void. It's a room full of things, with the lights off. Which is why this isn't a story that ends in despair, even though it spent a lot of time in the dark. The wall that kept us out is finally cracking. The cheap robots, the swarms, the software that can watch what we couldn't, the map creeping toward completion. For the first time since we started trying, the numbers can actually move. The blankness we've been staring into might turn out to be less a permanent condition than a snapshot of the moment right before the tools caught up. We are maybe standing at the last moment when the honest answer to how much of the ocean have we seen is still almost none. So picture it one more time. A single ROV, kilometers down, in water that has never known light. Its lamps carve out a small circle of illuminated ground, a lane of gray seafloor, a drift of marine snow, the edge of something moving at the boundary of the beam. And then, pull back. Watch that circle of light shrink as the black expands around it, until the lamp is a pinprick, and then almost nothing. One faint glow, suspended in a darkness the size of 2/3 of the planet. That pinprick is everything. That narrow beam is the entire history of us actually looking at the deep. 70 years of it, all our dives and machines and nerve, adding up to one small light in an ocean that goes dark in every direction for thousands of kilometers. That's the honest number, not 5%. A pinprick of light, and all around it still waiting. The largest unseen space on Earth.